Okay, let's figure out why those are wrong. What? That's exactly what I did. Oh my gosh, this is messing me up because I don't have my pinned tabs for some reason. Every time I... Let me try something. What the heck? My Safari crashed because I was pinning tabs. This is awful. Oh my gosh, everything's broken now. There we go, jeez. Now everything's back. There's no way this is faster. What? What is this? What does this mean? I'm so confused. Yeah, you told me to use remove. Oh my gosh. I'm so done. Then I have to use this dumb solution. It's like, oh my gosh. This is dumb. How's it? Watch, this is gonna work. So stupid. What am I doing wrong? I literally don't. Oh, this is so stupid. Bro. Of course. Of course. Of course. That was awful. Way too much time. Way too much time. Okay, contains duplicate. We're going to make a hash set with integers called set. And then we're going to iterate through all the numbers. And then if we cannot add in the set the current number, we're going to return true. Otherwise, we're going to return false. This occurs in O of n time and O of n space. Valid anagram. We're going to make a frequency array with integers that has 26 slots, and we are going to iterate through the characters in s.length. Something to note is that if s.length does not equal t.length, you cannot have an anagram. For each character in S, we're going to increment, and for each character in T, we are going to decrement. And then we're going to iterate through the entire length of the frequency array, and if any of the values do not equal 0, we're going to return false. Otherwise, we will return true. This occurs in O of n time and O of 1 space. So for toSum, we're going to cache previously iterated values in a hash map called cache. And we're going to iterate through each value in nums. And we're going to calculate a complement that equals the target minus the current number. And if the cache contains the complement as a key, we're going to return a new array that has the current index and the cache's value at the complement. Otherwise, we are going to take the cache and put in the current value and the current index. And then we will return an empty array as an exit condition. This will occur in O of n time and O of n space. Group anagrams. Oh my gosh, it's right there. So what we will do here is we will create a hash map that uses a string as a key and a list of strings as a value. And we're going to call it groups. And then we will iterate through all the strings in the strings array and make a frequency array for each string. For the length of the string, we're going to calculate the frequency of each character in the given string and increment it. And then we are going to make a key out of that frequency by converting the array to a string. If the map does not, or sorry, if the groups do not contain the key that we have made from the frequency array, we're going to take the groups and put in the key and a new array list of strings. And then we're going to take the groups, get the key, and then add the current string. Then we can return a new array list of the group's values. So this will occur in O of n time, or O of n times m time, where n is the number of strings and m is the average length of each string. And the space complexity will be O of n, where n is the number of strings. So here we're going to make a list of integers that are in an array and call it frequency, and make it a new array list of the size nums.length. And then we're going to make a hash map that stores an integer and an integer called counts, and make a new hash map. So for each number in nums, we're going to take counts and we're going to put in the current number, and counts get or default the current number, or 0 plus 1. And then for each value in counts, we're going to take the key and the value, and we're going to take the frequency of the or we're going to check if the frequency of the value minus 1 equals null. If it does, freq value minus 1 will equal a new array list. And then we'll take freq value minus 1 and add the key. And then we're going to iterate through the frequency array backwards. And if the frequency of the current iteration does not equal null, we are going to create an output array. And we're going to keep track of the current index of that output array. If the frequency of the current index does not equal null, we're going to take the current value, or we're going to iterate through the list of values in the frequency. And we're going to take the output, take the output's index, increment it once, and set it to the current value in the array list. And if the index equals k, we're going to return the output array. Otherwise, we're going to return the output array. So this occurs in O of n, here O of n here, O of n here. Yeah, so this is O of n, where n is the number of numbers in the array, and O of n space. So for encode, we're going to create a string builder called string builder, set it to a new string builder object, and then iterate through all the strings in the array. We're going to take the string builder and append the current string's length, append a delimiter, which I'm going to use the pound key, and then append the string itself. And then we will return the string builder's value as a string. For decode, I'm going to keep track of the integer I, and I'm going to say while I is less than string.length. I'm going to make int j equal I, and while string.char at j does not equal pound, I'm going to increment j. And then I'm going to take the length, and then when we hit the pound, we know the length of the array. So I'm going to create a variable called length and make it equal to integer.parseInt the string.substring ij. I'm going to increment the j one more time, and then I'm going to take the output list that I will now declare with string output equals new array list, and then I will take the output and add the string.substring j plus length, and then make I equal j, and then return the output. This is I plus 1. Never mind. There you go. So encode is O of n, where n is the number of strings. And space complexity is O of n, where n is the number of strings. Actually, it might be, space complexity might be, you can consider n times m, where n is the number of strings and m is the average length of each string. And then for decode, time complexity is O of n, where n is the number of characters in the string, the length of the string. And then space complexity is O of n, where n is the number of words. So for this, we're going to create an output array. This an array of integers with the length nums.length, and we're going to fill the output array with 1. We're going to iterate from 1 to the length of the nums array. I'm going to separate it to its own variable to avoid duplication of code. And then the current value is going to equal the previous output value times the previous numbers value. And then I'm going to have a rolling product equal 1, and I'm going to iterate through the array backwards. And then I'm going to make output times equal output or rolling product, and I'm going to take rolling product and multiply it by the current number, and then return the output. Oh, sorry, output I. So here space complexity is O of n, time complexity is O of n as well, where n is the number of numbers in the array. Valid Sudoku, this is just Sudoku validation, so I'm gonna iterate through the board. J equals board I dot length, J plus plus. Set integer set x. Set integer set x equals new hash set. Set integer set y equals new hash set. Char cur x equals board I j. Char cur y equals board j I. If cur x does not equal a period, and set x cannot add cur x, I'm going to return false. And we do the same for cur y. So if cur y does not equal a period, and set y cannot add cur y, we're going to return false. And then I'm going to iterate through the subgrid. So I'm going to iterate through the rows, board.length, I plus equals 3, and 4 int j, j equals 0, j has to be less than board I.length, j plus equals 3, and then 4 int row equals I, row has to be less than I plus 3, row plus plus. For int call equals j, call has to be less than j plus 3, call plus plus. And we're going to make a set of characters called subgrid and make it a hash set. And then we're going to do the same thing. So char cur equals board row call. If cur does not equal period and subgrid can add cur, we're going to return false. Sorry, can't add cur. And then after that, we're going to return true. But I made a mistake here. These integers should be characters. And then we should all be good. To be honest, I don't know what the time complexity and space complexity is, because technically all Sudoku grids are going to be 9 by 9. So this could be O of 1 for both time and space complexity, or it could just be O of n times m, where n is the number of rows and m is the number of columns. Okay, why is it doing this? Yeah, it looks like it's considering it as O1. Oh my gosh. I'm just gonna reload this. Yeah, sure. Longest consecutive sequence. Okay, so here we're going to make a set of integers called set and make a new hash set. And we're going to iterate through all the numbers and add those values to the set. Now we are going to iterate through all the numbers once again. And if the current if the set does not contain the current number minus 1, we know that it's the smallest number in its relative subsequence. So we're going to take int cur equals I'm going to actually do that here. Int cur equals nums I minus 1, or nums I, and then we're going to do cur here. So set does not contain cur minus 1, while cur or set dot contains cur, I'm going to increment the counter here, and then I'm also going to store a max that is equal to 0. So here I'm going to increment the counter, so counter plus plus, and then I'm going to say cur plus plus as well, and then I'm going to do max equals math.max between itself and the counter variable that I calculated, and I'm going to return max at the end of the algorithm. So this, is it contains? Yeah, it is. Okay. Yeah, so this occurs in O of n, and time complexity is O of n. This is O of n because we, this will, wait, what the? This will, oh, I forgot. There's something, they added an edge case. I forgot what it was, though. I forgot the edge case that they added. It's super stupid, but yeah. Let me ask what the difference is between these. Oops. I'm gonna get rid of this. How much faster is it though? So instead of being O of 2n, it's O of n. Yeah, that makes sense. So here we're gonna have, I get it now. We have int max equals 0, set integer set equals new hash set. Oops. Set integer set equals new hash set. For int num in nums, set to add num. For int num in set. If set dot contains num minus 1, if set does not contain nums minus 1, while int counter equals 0, while set dot contains num plus counter plus counter plus plus max equals math.max max counter return max. Yeah. Now that I think about it, that makes sense. This is like twice as fast. So, okay. Two pointer, valid palindrome. So here what we're going to do is we're going to have a left pointer and a right pointer. The left will equal 0 and the right will equal s dot length minus 1. And while left is less than right, what we're going to do is check if the left character is a letter or digit. And if it isn't, then I'm going to increment left. And then we do the same with right. So if the right character is not a letter or digit, we're going to decrement right. Otherwise, if the character at the left index equals the character at the right index, I'm going to increment left and decrement right. And then if that doesn't work, then I'm going to return false. And then we'll return true after all the processing. Char at. Oh, I also need to make s equal s dot to lowercase. There we go. So this is going to happen in O of n. Time or space complexity is O of 1. To sum, but input array is sorted. So what we're going to do here is I will have a left pointer and a right pointer that equals numbers dot length minus 1. And then while left is less than right, I'm going to calculate the current value, which is numbers left plus numbers right. If the value equals the target, I'm going to return a new integer array with left plus 1 and right plus 1. Otherwise, if the value is less than the target, I'm going to increment left. And if the value is greater than target, then I'm going to decrement right. And then at the end of the day, I'm going to return an empty array just in case as an exit condition. There we go. That happens in O of n time and O of 1 space. Oh, this one might be tricky. So what I'm going to do is I'm going to sort the array first because I want to be able to, the easiest way in my view for me to be able to determine if there's a duplicate is if I sort it and then I can compare adjacent values on whether or not they're the same. So I'm going to sort and then I'm going to create my output array. So list integer output equals new array list. And then I'm going to iterate through the array. And if I equals 0 or nums I does not equal nums I minus 1, we know that we do not have duplicate values. I'm going to make a left pointer, which is going to equal nums I. Oh wait, sorry. It's going to be equal I plus. It's going to equal I, and then I'm going to make a right pointer, which is equals to nums.length minus 1, and then a target, which equals 0 minus nums I. And I believe this is going to be I plus 1. And then while left is less than right, I'm going to calculate the complement, which equals nums left plus nums right. And if the complement equals the target, I'm going to make a new list called list. I'm going to add nums I, add nums, oh wait, no. Am I in the indexes? No, I'm not. Nums left, and then add nums right, and then add that array to the output array. Output to add list. And then, while left is we're going to do some processing to help help lower load. So while left is less than right still, and nums at left equals nums at left plus 1, we're going to increment left. And then while left is less than right and nums.right equals nums.right minus 1, I'm going to decrement right and then increment left and decrement right one last time, because we want to move outside of the duplicate values. Otherwise, if complement is less than target, I'm going to take left and increment it. And then if complement is greater than target, I'm going to take right and decrement it. And then I'm going to return output, which I think needs to be moved down a level. Yeah. There we go. So this occurs in O of n log n here, O of n, O of n. So O of n squared, and then the space complexity is O of n, I believe. In the worst case. O of n squared, okay, perfect. Space complexity should just be O of n. Yeah, for output list, beautiful. Container with most water. So here, I'm gonna have a max variable as my output, and then a left pointer and a right pointer, which is going to equal heights.length minus 1. And while left is less than right, I'm going to iterate. So I'm going to calculate the current water, which is going to equal the minimum between the heights of the left pointer and the right pointer, multiplied by the right pointer minus the left pointer. And it's 0 indexed, so for example, here we'd have 0 and what's the length of this? 1, 2, 3, 4, 5, 6, 7, 8, 9. 0 and 8. So that'd be 8. And then we have 1 and 8, which is 7, which is correct. So we don't need to add anything for one-off errors. I don't believe so. And then I'm going to take max and make it equal to math.max between itself and the water calculation that we just made. And if the height of the left pointer is less than the height of the right pointer, I'm going to increment left because we want to maintain the highest height of the two. And then if the height of the right pointer is less than the height of the left pointer, I'm going to decrement right to do the opposite. And then I'll return max at the end of the day. Height. There we go. This occurs in O of n time and O of 1 space. Trapping rainwater. Okay. So here we're going to create a water variable to store the water. I'm going to have a left pointer, which is going to equal 0, a right pointer, which is going to equal 0, and then a max left value that is going to equal the current value of the left pointer, a max right value, which is going to equal the current value of the right pointer. And that should be it. So while left is less than right, what I'm going to do is I'm going to check if the height of the left value is less than the height of the right value. If that is the case, that means I know that anything on the left, or any water that I capture on the left, is guaranteed to have a wall on the right that's higher than it so that we can capture it. And what I'll do here is I will make max left equal the max between itself and the current height of the left pointer. And then I'm going to add to the water that we trap the max left value minus the current height. And then I will increment left. Otherwise, I'm going to do the opposite. So I'm going to take the max right, calculate the max between its own value and the right pointer's value. And then I'm going to add to the water the highest right value that we've encountered minus the current right value that we are encountering, and then decrement right. And then at the end of the day, I will return water to have our value. This occurs in O of n time. What? What? Am I dumb? What? Oh, okay, there we go. Okay, something's wrong. This should work. What is going on? It looks like I'm never adding any water. Wait, what am I doing wrong? Do I have to do this? Wait, what am I doing wrong? What the heck? I'm so confused. Oh, shoot. There we go. Jeez. That was a silly mistake. Okay, that's done. Stack. Valid parentheses. So what we're going to do here is make a stack of characters. Call it a stack. New stack. I'm going to iterate through all the characters in the string. Store the current character. And if the current character, if the stack is empty, or the current character equals an opening form of a parenthesis, I'm going to take the stack and push the current value. Otherwise, if the current value is a closing parenthesis, closing rounded parenthesis, and the current value at the top of the stack equals its complement, then I'm gonna pop, and I'm gonna do this for all the different types of brackets. And then otherwise, I'm gonna push onto the stack, and then I will return whether the stack is empty or not, and that will be my value. Oops. Oh, it's because of this. There we go. Beautiful. Occurs in O of n time, O of n space. I need to go to the bathroom. Okay, min stack. So here I'm going to have two instance fields. One is going to be a traditional stack that stores all the values, called stack, and the other will be a min stack that only stores the minimum values, called min stack. This dot stack will equal a new stack. This dot min stack will equal a new stack. And then we will process. So for pushing, this is the important part. If the min stack is empty, or the current value is less than or equal to the min stack's top value, we're going to take that min stack and push the value. And then we're just going to push any value to the traditional stack. For popping, we want to check if the traditional stack's value equals the min stack's value. And we want to use the equals operator because the wrapper class for the integer actually, I believe if it has the same two integers in it, it won't equal because the references are different. So we have to use the equals. We have to do a deep comparator of the integer values of the stack and the min stack. If they equal, we're going to take the min stack's value and pop it, and then we're going to take the traditional stack's value and pop it whenever. For the top, we're going to return the top of the traditional stack, and to get the min, we're going to return the top of the min stack. So here we have the min stack class with a stack and a min stack. Push will take O of n time and O of 1 time, and O of 1 space. Pop will do O of 1 time and O of 1 space. Same with top and get min. However, the min stack class as a whole will take O of n space as you push and pop and execute these functions. So yeah, let me run it. There we go. Evaluate Polish reverse notation. Okay, perfect. So here I'm going to use a stack that stores integers called stack. And then I'm going to iterate through all the tokens and make a switch statement for each token. If the token equals a plus, I will take the stack and push the top two values in the stack added together. If the values are a subtraction sign, I will take the first term, the second term, and the first term, and push term 1 minus term 2 onto the stack and break. And we have to do this because subtraction isn't a commutative property, addition is. So if I take 3 plus 4 and I add that together, we'll get 7, and if I take 4 plus 3, it'll equal 7. However, with subtraction, that isn't the case. 3 minus 4 will be negative 1, and then 4 minus 3 will be 1. So it's important. Order matters in terms of subtraction, and we'll see the same happen with division as well. So here we have to take the second term first, and then the first term, and then subtract it. Yeah. So if we equal multiplication, then we can, multiplication is commutative, so we can just take the values and multiply them together. And break. And then if we encounter division, then we have to separate the numerator and denominator. So I believe, let's think about this. Let's see. So here it'll be 4, 13. So it's 13 divided by 5. So the numerator will be the first value. And numerator equals stack.pop. And then the denominator will equal the second value. And we will just push the numerator divided by the denominator. Break. And then we will have a default case where if none of these If none of these conditions are satisfied, I'm going to take the stack and push the string's integer value, the token's integer value, because if none of these cases are passed, then we know we have a number, and then I will return stack.peak. Oh, integer.parse int. What am I doing wrong? Division might be wrong. Yes, division is wrong. It's this. Let me check if subtraction's wrong too. Subtraction is right, I believe. Yeah, there we go. Beautiful. O of n time, O of n space. Generate parentheses. So this is more of a backtracking problem, actually. What we can do is we'll call a backtracking method that we create, and we want to keep track of opening parentheses, closing parentheses, the number of parentheses that we have, and our output array, which we will declare and initialize right here. So we're going to make an output array and pass it into the backtracking and return the output array. For the backtracking method, we're going to have the number of open parentheses, the number of closing parentheses, the number of parentheses overall, and the output array. Output, yeah. So if open plus close equals, actually I think we want a string builder object as well. So that'll be here. String builder. So if the string builder's length equals n times 2, we know that we have created a parenthesis. We've generated a proper parenthesis, or a parenthesis of the proper length at least. So we're going to add to the output a new string that has string builder.toString in it. Otherwise, what we're going to do is, if open is less than n, I'm going to add an opening parenthesis. So I'm going to backtrack again with open plus 1, close, n, and then string builder.append opening parenthesis. And I'm going to add that string builder back here, and then the output array, obviously. And then at the end, once that backtracking is done, I want to actually delete that opening parentheses that I just added. So delete char at string builder.length -1, and that will delete that character. Now now we need to close the parentheses. So if the closing parentheses is less than the opening parentheses, we want to start closing, because we don't want to close more parentheses than we have opened, and we don't want to open more parentheses than are available to us. So these are very dependent on each other, which is important to understand when understanding the code here. So we'll have a string builder, and we'll add a closing parenthesis to it, and then we'll backtrack again. We'll pass an open, close plus 1, because we just added a new close parentheses, the string builder object, and the output array. And then we're going to take the string builder and delete the character at the end of the string builder. So string builder.length -1. And that will be generate parentheses. So this occurs in O of, I believe, n to the, wait, what? Oh, whoops, string. Output. To be honest, I don't know what the time complexity here is. With the time complexity with all these backtracking things is kind of hard for me, at least. If I were to take an educated guess, space complexity is definitely n times 2. Oh wait, no. Space complexity is n. It might be n factorial. I don't know. We have two different paths here, so it might be 2 to the n for time complexity, and then n factorial for the. I don't know. Let me think a little harder before. Stack, or what's it called? The stack, the call depth. The call stack depth will be. I don't even know. I really don't know. Yeah, I knew it was something like this. So it's 4n, 4 to the n. Why though? Yeah, recursion depth is 2. Stack space is O of n. This is tricky. I'm not gonna trip about this too much. Daily temperatures. Okay, so we're gonna make a stack. Have it store integers, call the stack. And then for each, we're gonna iterate throughout the entire temperatures array. And if the stack is empty, or the current temperature is less than the temperatures in the stack, then we're going to take the stack and push the current index. Otherwise, while the temperatures of the stack are less than the current temperature, then I will start populating the output array. So output stack.peak equals I minus stack.pop. And then I'm going to return output. Something is wrong here. I don't have a semicolon here. Okay. Empty stack exception. Stack that is empty, and well, the stack isn't empty. So what did I do? Oh, wait. I can just reframe this. So while the stack is not empty and the temperatures of the stack are less than the current temperatures, then we'll make that calculation. Otherwise, stack.push I. And we don't need to do any of that bogus. There we go. Car fleet cheese. So how do we do this? I'm going to create a hash map with the current position, or the car in the current, or the car's position, and the amount of time that it'll take to reach the target. And I'm going to name this time. Make it a new hash map. And then I'm going to iterate throughout each value in both speed and time. So I'm going to take time and put in the current position, and as the value I will make the calculation of how long that position takes to reach the target. So I'm going to take target minus position I divided by speed, and I will make this a double and typecast it. Then I will sort the positions array and iterate through it backwards. And then I'm going to just make int n equals speed.length, so I can avoid writing duplicate code. So int I equals n minus 1, I has to be greater than 0, I minus minus. Then what? Then what? Oops. Then how many fleets there? Okay. So I'm gonna have a variable called fleets equals 0, and then a double for the previous time equals 0.0. So if the current position's time, if time.get position I, if the current position's time to get to the target is greater than the previous time, then I'm going to implement fleets increment fleets, and then make previous time equal time.get position I. And then I think that's it. Return fleets. That should be it. Oh, sorry, speed I. There we go. So this occurs in O of n log n because of the sorting. This is n of n, or sorry, this is O of n. This is also O of n, where n is the number of cars. But we have to make it n log n due to the sorting. And then space complexity is O of n as well for the time hash map and the output array. Or actually, there is no output array, sorry. Largest rectangle histogram. Okay, so here we're going to make a stack full of integers and call it stack. New stack. And then I'm also going to make an index array. And then I'm going to iterate through heights. So while index is less than heights length, if the stack is empty, or if the height of the current top of the stack is less than or equal to the height of the current index, I am going to take the stack and push the current index and increment it at the same time. Otherwise, I'm going to calculate the width, which is going to equal, the height is going to equal the top of the stack, and then the width is going to equal whether the stack is empty or not. It's going to equal index or index plus 1. No, index minus 1, I think. Minus stack.peak, yeah. And then int output equals 0. So output is going to equal the max between itself and the height times width. And then, while the stack is not empty, return output. The reason why we do this is because if we end in a monotonic stack, heights, I guess I should probably explain the intuition behind this though. Oh, if stack is, jeez. If stack is empty, we want index minus 1, otherwise index minus stack.peak. Oh, jeez. Empty stack exception. I just asked if the stack was oh. Okay, something about my width calculation is definitely off. I literally, I know it's the width. I just don't know how to calculate it. Oh my gosh. Why is it like that? What am I doing wrong? What am I doing wrong? Oh shoot, it's heights here. I'm pretty sure. Yeah. There we go. Let's do that one more time, just to double check. Into index 0 equals 0. Stack integer stack equals new stack. While index is height not length. If stack is empty or height stack.peak is less than or equal to heights index, stack.push index plus plus. Else int height equals heights stack.pop, and width equals width, and width equals stack.is empty. Index, otherwise it's index minus stack.peak minus 1. Why is it minus 1? So this is the difference between that, minus 1, because it's 0 indexed. Zero, 1, 2, 3. Oh, because index is it really should be index minus 1 minus stack.peak. That might break it though. Just math that output equals math.max max output height times width. Let's try it. Index minus 1 minus stack.peak. Let's see what happens. While stack.is is empty. Return output. Oh yeah, it does work. Okay. Yeah, it needs to be index minus 1 because the index is ahead by 1. That's why. Alright. Binary search. Jeez. Let's see. And left equals 0 and right equals nums on length minus 1, while left is less than right. And middle equals left plus right minus left to avoid integer overflow. If nums middle equals target, return middle. If, oops, there's square brackets. If nums middle is less than target, we're gonna make left equals middle plus 1, else right equals middle minus 1. Return negative 1. Oh wait, I need the equals to sign here. There we go. Search 2D matrix. So this is the same thing, but we just iterate data structure basically. Matrix.length times matrix 0.length minus 1. While left is less than right, and middle equals left plus right minus left divided by 2, and row equals middle divided by matrix 0.length, and call equals middle mod matrix 0.length. If matrix row call equals target, return true. If matrix row call is less than target, left equals middle plus 1, else right equals middle minus 1. And then I need to do the same thing again where I make it less than or equal to, and then I return false if we don't find it. There we go. Beautiful. All of that was O(n) or log n. Coco eating bananas. So here we're gonna make a minimum integer and a maximum integer, and then for int bananas in piles, max is gonna equal math.max max bananas, while min is less than or equal to max, and average equals min plus max minus min divided by 2 for int bananas in piles. In hours equals 0, hours plus equals math.ceil banana or double bananas divided by average. If hours is less than or equal to h, if we ate it too fast, we need to make max equal average, else min equals average plus 1. Return max. And this will not be less than or equal to, this will just be less than, because we're waiting for the values to converge. Boom. That's the first time I think I've gotten it first try. Wow. Log n. Find minimum and rotated sorted array. So here we're going to have in left equals 0 and right equals nums.length minus 1. Length minus 1, while left is less than right. It's going to be less than or equal to, and middle equals nums left. Oh, yeah, nums left plus nums right. Wait, whoa. And middle equals left plus right minus left divided by 2. If nums middle is less than, no, is greater than nums, no, this is wrong. If nums left is greater than nums middle, then maybe this isn't less than or equal to. If nums left is greater than nums middle, left equals middle, else right equals middle minus 1. Return left. Oh, I get it. So while left is less than right, and middle equals left plus right minus left divided by 2. If nums middle is greater than nums right, left equals middle plus 1. Else right equals middle. Return nums right. There we go. We have to start on the right side because it's the larger side. I forgot about that. Search and rotated sorted array. Okay, so in left equals 0 and right equals nums.length minus 1. While left is less than right. And middle equals left plus right minus left divided by 2. If nums left is less than or equal to nums middle, else if nums left is less than target, no. If target is less than nums left, or nums middle is less than target, left equals middle plus 1, else right equals middle minus 1. if target is less than nums middle, or nums right is less than target, right equals middle minus 1, else left equals middle plus 1. Return -1, and then here it's if nums middle equals target, return middle. Yeah. Oh my goodness. This is less than or equal to. There we go. Log in again. Time-based key value store. Okay. This is tricky. It's like map, string, list. List of pairs. Yeah. Map equals new hash map. This dot map equals new hash map. I actually don't need this. Okay. So if this dot map does not contain the key, this dot map dot put key new array list. This dot map dot get key dot add new pair value timestamp. What is with me in the square brackets right now? Okay, now we need to define pairs. So we have class pair, public string value, public int timestamp, public pair, string value, int timestamp. This dot value equals value. This dot timestamp equals timestamp. Yeah. Then get. So if this dot map dot does not contain the key, we're going to return an empty string. Otherwise, we'll return binary search for this dot map dot get key and timestamp. Public string timestamp or binary search. We have a list of pairs called list, and then we have timestamp. So in left it will equal 0, and right will equal list.size minus 1, while left is less than right, while left is less than or equal to right. In middle equals left plus right minus left divided by 2. If list.get middle.timestamp equals timestamp, return list.get middle.value. If list.get middle.timestamp is less than timestamp, if the timestamp is less than timestamp, we're going to make right equals middle minus 1, else left equal middle plus 1. Return, if right is greater than or equal to 0, we're going to return list.getRight dot value. Otherwise, we're going to return an empty or a blank blank string contains key. Uh-oh, what did I get wrong? Set foo bar 1, set get foo 1. Set foo get foo 3. Okay, so this isn't working. I'm dumb. This is it. There we go. There we go. Geez, medium two-sided arrays. That one is a shocker, man. Length 1 equals nums 1 to length. Length 2 equals nums 2 to length. If length 1 is greater than length 2, return find median sorted arrays, nums 2, nums 1. Int left equals 0, int right equals length 1, int half equals length 1 plus length 2 divided by 2, while left is less than right. Int partition 1 equals left plus right minus left divided by 2. Int partition 2 equals half minus partition 1. Int left 1 equals partition 1 equals 0. Then integer dot min value, otherwise partition 1, otherwise nums 1 partition 1 minus 1, and right 1 equals partition 1 equals length 1, integer dot max value, nums 1 partition 1 minus 1, int left 2 equals partition 2 equals 0, integer dot min value, nums 2 dot partition 2 minus 1, and right 2 equals partition 2 equals length 2, integer dot max value, nums 2 partition 2 minus 1. If left 1 is less than or equal to right 2 and left 2 is less than or equal to right 1, if int total length equals length 1 plus length 2, total length, and then here I think I did this wrong. I'm going to do total length plus 1 divided by 2 just to round up, and then if total length mod 2 equals 0, actually no, if it equals 1, return double math.max left 1 left 2, else return double math.max left 1 left 2 plus math.max right 1 or min, sorry, right 1 right 2 divided by 2, else if left 1 is greater than right 2, then partition 1 equals left equals partition, right equals partition 1 minus 1, else left equals partition 1 plus 1. So left return 0.0. What? Oh, shoot. There we go. So here we just track the minimum. Yeah, prices can only equal 0. So for int I equals for int price and prices. I wonder if I can do it this way. If price is less than min, min equals price. Else profit int profit equals 0. Profit equals math.max profit and price minus min. Return profit. What the? Oh. There we go. O of n, O of one space. So we're gonna have a map of characters and integers. Last occurrence equals new hash map. For int I equals 0, I has to be less than s dot length, I plus plus. If last occur, char occur equals s dot char at I. If cur, oh wait, I'm dumb. Int left equals 0, int output equals 0. For int right equals 0, right has to be less than s dot length, right plus plus. Char cur equals s dot char at right. If last occurrence dot contains key of cur, then left will equal math.max left and last occurrence dot get cur plus 1. And then output is going to equal math.max between output and right minus left plus 1. And then last occurrence dot put cur and then right. Return output. Oh my gosh. There we go. So in left equals 0 and right equals 0. While left is less than, what? You could choose a character. Oh, I think this is it's like max freak equals. No.
frequency equals new int 26. Max frequency equals 0. Left equals 0, right equals 0, while left is less than s.length. Yeah, I think frig s.char at right minus a plus plus max freq equals math dot max frequency s.char at right minus a if max frequency minus k it's like if right minus left plus 1 is greater than max frequency minus k. No. If right minus left minus max frequency right minus left plus 1 minus max frequency is greater than k, freq s.char at left minus a minus left plus plus, and then the output equals 0. So then output will equal math.max output right minus left. I think it's left plus 1, like this. Oops. There we go. Nice. Permutation in string. Oh. So we're going to make a frequency array. Wait. So if s2.length is less than s1.length, we're just going to return false. Freq1 equals new int 26 and freq2 equals new int 26 has to be less than s1.length. Freq1 s1.char at I minus a plus plus freq2 equals s2.char at I minus a plus plus if arrays.toString freq1 that equals arrays.toString freq2 return true for int I equals s1.length. I has to be less than s2.length a plus plus. Freq1 s2.char at I minus s1.length minus a minus freq1 s2.char at I minus a plus plus if arrays.toString freq1 that equals arrays.toString toString frig2 return true, return false. There you go. Oh, shoot. There we go. Beautiful. Minimum window substring. Oh my gosh, these are the deck problems, bro. Let me try this one. This one's hard too, man. Oh, all these are hard. This one's weird too. So we're gonna make a frequency array 128 because it includes upper and lowercase. For in I equals 0, I must be less than t dot length, I plus plus, freq t dot char at I minus a plus plus. Right equals 0 as well. And required equals t dot length. Int min start equals 0. Int min length equals integer max value, while right is less than s dot length. Frick s dot char at char cur right equals s dot char at right. If recur right minus a is greater than 0, required minus minus cur right minus a. Wait, I don't think I even need to do the minus. I think I can just delete all those, yeah. Recur right minus minus right plus plus, while required equals 0 if right minus left is less than min length equals right minus left, min start equals left. Frick cur left, well, char cur left equals frick s dot char at left, frick cur left plus plus, if frick cur left is greater than 0, required plus plus. left plus plus. Return main length equals integer max value. Otherwise, s.substring min start plus min length.
Oh my gosh. Too nice with it.
Deck integer deck equals new linked list. For I equals 0, I equals nums out length, I equals plus. Deck that is empty or size. Deck dot peak first is I minus k minus 1. Deck dot pull first. And then while deck is not empty and deck dot peak last is less than or equal to less than nums I think it's like nums deck dot pull last deck dot offer last I if I is greater than or equal to k minus 1. Output I minus k plus 1 equals deck dot peak first nums deck dot peak first, something like that. Return output int output equals new int nums dot length minus k plus 1.
No way! No way! Oh, never mind. Must be something's off. It's probably this. Deck dot peak first 0 1 minus 0 or 1 minus 1 minus 1 1 minus 1 minus 1. That's negative 1. Jeez. I think it's just k minus 1. What if isn't it just like this? Oh, I don't know this one.
I don't think it's this. That's kind of crazy. I was not prepared to like actually get those first try too. Oh, okay. Oh, linked list is crazy too. Alright, list node prev equals null. While head does not equal null. List node next equals head dot next. Head dot next equals prev. Prev equals head. Head equals next. Return prev. Return prev. Boom, 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 boom. Merge two sorted lists. List node list equals new list node. Wow. List 1 does not equal null and list 2 does not equal null. If list 1 dot val is less than list 2 dot val, list dot next equals new list node, list 1 dot val, list 1 equals list 1 dot next, else list dot next equals new list node, list 2 dot val, list 2 equals list 2 dot next, list equals list dot next. While list 1 does not equal null, list dot next equals new list node, no list 1 dot val, list 1 equals list 1 dot next, list equals list dot next. While list 2 does not equal null, list dot next equals new list node, list 2 dot next, or dot val, list 2 equals list 2 dot next, list equals list dot next. Return dummy dot next, and then here, oops, and then here we'll make a dummy node. So we'll have list node dummy equals just list. Beautiful. Linked list cycle. List node slow equals head, list node fast equals head, while fast does not equal null and fast dot next does not equal null, slow equals slow dot next, fast equals equals fast dot next dot next. If slow equals fast, return null or return true. If we ever exit, we return false. There we go. Okay. Reorder list. Oh geez, this one's kind of hard, right? Yeah. List node cur equals head. No, wait, list node slow equals head, list node fast equals head, while fast does not equal null and fast dot next does not equal null, slow equals slow dot next, fast equals fast dot next. Okay. Then list node cur, list node. So slow dot next equals null. I know that. This node reverse equals slow dot next, like this. List node cur equals head. No, wait. List node prev equals null. Slow dot next equals null. While reverse does not equal null. List node next equals reverse dot next, reverse dot next equals priv, priv equals reverse, reverse equals next. So then this node cur equals head, this node and then prev is there. So then while cur does not equal null, this node temp1 equals cur.next, this node temp2 equals priv.next, cur.next equals priv, priv.next equals temp1, cur equals temp1, prev equals temp2. That's it. And prev does not equal null. There we go. There we go. Beautiful, 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 beautiful. Okay. So we'll have list node slow equals new list node, or no, list node dummy equals new list node. Dummy.next equals head, list node slow equals dummy, list node fast equals dummy, while for in I equals 0, I has to be less than n plus 1, I plus plus, fast equals fast.next, while fast does not equal null, slow equals slow.next, fast equals fast.next, slow.next equals slow.next.next, and then return dummy.next. Beautiful. Okay. So here there are two ways. I'll do both. Node map equals new hash map. Node cur equals head. While cur does not equal null, map.put cur new node cur.val. Cur equals cur.next, and then cur will equal head again, and while cur does not equal null, map.get cur dot actually wait, if cur.random does not equal null, map.get cur.random equals map.get cur.random. Cur equals cur.next. Oh wait, actually I need to do map.get cur.next equals map.get cur.next. And then return map.get cur head. There we go. And then the other way is to do node equals, or node cur equals head. If head equals null, return null. While cur does not equal null, node next equals cur.next. Cur.next equals new node cur.val. Cur.next.next equals next. Cur equals cur.next.next. And then cur equals head again, while cur does not equal null. if cur.random does not equal null, cur.next.random equals cur.random.next, and then cur equals cur.next.next, and then cur equals head, while cur does not equal null, cur.next equals cur.next.next, and then if cur.random cur.next equals cur equals cur.next, return cur, return head. This is wrong. I think there's something wrong here. Yeah. Cur.next does not equal null. I wonder what happens here. Staying with this head. I'm missing a check somewhere. What am I missing? I haven't done this since December. Jeez. Whoops. Okay. So cur equals head, node copy equals cur.next, node copy head equals cur.next, while copy does not equal null, copy.next equals copy.next.next, copy equals copy.next. I wonder, this is probably gonna break too. Yeah. So like if copy.next does not equal null, what the heck is going on here? Why do we have to split both of them? What the heck? Something else must be going on. Oh my gosh. Do I need this then? I don't think I need this.
Why do you have to split cur and copy at the end? I guess. Okay, list node, last equals new, list node, remainder equals 0, while L1 does not equal null and L2 does not equal null. List.next equals new list node, L1.val plus L2.val plus remainder divided by 10. Remainder equals L1.val plus L2.val plus remainder mod. No, divide by 10. This one's mod 10. Yeah. List equals list.next, L1 equals L1.next, L2 equals L2.next. While L1 does not equal null. Wait. Yeah. While L1 does not equal null. List.next equals new list node, L1.val plus remainder mod 10. Remainder equals L1.val plus remainder divided by 10. List equals list.next, L1 equals L1.next. L2 does not equal null. List.next equals new list node. L2.val plus remainder mod 10. Remainder equals L2.val plus remainder divided by 10. List equals list.next. L2 equals L2.next. Yeah, here. If remainder does not equal 0, then list.next equals new list node remainder return. List node dummy equals list. Return dummy.next. Beautiful, beautiful. Okay. Oh, this stuff's dumb. So and fast equals nums 0. Do slow equals nums slow. Fast equals nums fast. Wow. Slow does not equal fast. And then wow. And then fast equals nums 0. Wow, slow does not equal fast. Slow equals slow.next. Slow or nums slow. And then fast equals nums fast. Return, doesn't matter which one we return slow. Beautiful. Least recently used cache. So node or public node left, public node right,
public int capacity, public map, this dot left equals new node 0 0, this dot right equals new node 0 0, this dot left dot next equals this dot right dot prev, this dot right dot prev equals this dot left dot next. This dot capacity equals capacity, and then this dot map equals new hash map. Yeah, something like that. Get I think this might be node. Yeah. So I'll have class node here with some instance fields public node prev public node next public node or what int key public int value public node this int key int value this dot key equals key this dot value equals value public insert or void insert node 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 prev equals this dot node this dot no, that's not how it works. We gotta do it here. Okay, get. So if this dot map dot contains key remove this dot what do I do? This dot map node equals this dot map dot get key remove node insert node else if map does not contain it. Put actually let's do this public void remove node node prev equals node dot prev node next equals node dot next prev dot next equals next dot prev equals prev public void insert node this dot prev equals this dot right dot prev this dot next equals this dot right oops node so prev dot next equals node dot prev equals prev wait what prev dot next equals node next dot prev equals node dot next equals next node dot prev equals prev. Yeah, something like that. Now pudding. So this dot map dot size is less than this dot capacity, then this dot map dot put key new node node new node equals new node key value new node insert new node else node node oh my gosh. Okay, so this is bad wrong. If this dot map dot contains key else this dot mapped, okay, so then it'll be like node new node equals new node key value this dot map dot get or put key new node remove this dot map dot get key insert new node. Sure. If this dot map dot size equals is less than this dot capacity node new node equals new node key value this dot map dot put key new node else. This map dot put key new node insert new node node LRU equals this dot left dot next this dot this dot map dot remove LRU dot key and then node new node equals new node key value yeah, we can definitely just move this here. This dot map dot put key new node insert new node remove LRU, yeah, something like that. Okay. Can I make this cleaner? I feel like I can. Oh, whatever. Priority queue list node queue equals new priority queue. What the? Priority queue a dot val minus b dot val for list node list and lists q.offer list while q is empty. This node output equals new list. List equals new this node. List.next equals q.pull peak. If q.peak.next does not equal null, q.offer q.pull.next. Ah, shoot. Peak.next. Q.pull. Return list equals list.next. List node dummy equals list. Dummy.next. If list does not equal null. There you go. I'm not even gonna try this. I don't think it's worth trying this. This is like so ridiculously hard. Like, I'm not gonna be able to memorize all this. Yeah, I'm not gonna try that. Alright, trees. Okay. If root equals null, return null. Tree node left equals invert tree root right. Tree node right equals invert tree root left. Root left equals left. Root right equals right. Return root. Beautiful. Okay. Maximum depth binary tree. If root equals null, return 0. Equals max depth. Ooh. Return 1 plus math.max max depth root.right. Sorry, left max depth root.right. Okay. Diameter. Public int diameter. Public solution. This dot diameter equals 0. DFS root return this dot diameter. Public void DFS. No, wait, actually it's int. DFS int tree node root. If root equals null, return 0. And left equals DFS root dot left, and right equals DFS root dot right. This dot diameter equals math dot max. This dot diameter left plus right. Return math dot max. Return 1 plus math dot max left right. Okay. Okay. Balanced binary tree. If root equals null, return true. No, that's not it. Return DFS root equals, does not equal -1. Public int DFS tree node root. If root equals null, return 0. and left equals DFS root dot left, and right equals DFS root dot right. If left equals -1 or right equals -1, or math.abs left plus minus right is greater than 1, return -1. Otherwise, we're going to return 1 plus math.max left right. Okay. Same tree. Okay, so if P equals null or Q equals null, we're going to return P equals Q. And then if P.val does not equal Q.val, we're going to return false. Otherwise, we're going to return is same tree, P.left, Q.left, and is same tree with P.right and Q.right. Beautiful. Subtree of another tree. If subroot equals null, then return true. If root equals null, then return false. And then if root.val equals subroot.val and is same tree, root subroot, return true. Otherwise, we're going to return is subtree root dot left subtree subroot, or is subtree root dot right subroot. Public boolean is same tree, tree node t1, tree node t2. If t1 equals null or t2 equals null, return t1 equals t2. If t1.val does not equal t2.val, return false. Return t's same tree for t1.left, t2.left, and is same tree for t1.right, t2.right. There we go. Okay. Subtree lowest common ancestor. Okay. So if root equals null, we're going to return null. While root, I'm dumb. While root does not equal null, I don't need that because I have this. If root.val is less than p.val and root.val is less than q.val, if root equals root.right, else if root.val is greater than p.val and root.val is greater than q.val, root equals root.left, else return root, return null. There we go. Binary tree level order, okay. Some BFS. So here we're gonna have list, integer output equals new array list. If root equals null, then we're gonna return the output. Otherwise, we're gonna make a queue of tree nodes called queue and make it equal to a new linked list. Offer the queue the root, and then while the root or the queue is not empty, we are going to take the size, q.size, for int I equals 0, I has to be less than size I plus plus, and then take the current tree node, which is q.poll. If cur.left does not equal null, we're going to take the q and offer cur.left. If the cur.right does not equal null, we're going to offer the q cur.right, and then we'll take the we're going to take a level and add cur.val. And then we'll make a new array list right here. List integer level equals new array list. And then after that, we will take the output and add the level to the output and return the output. Right side view, this is the same thing. So if root, or shoot, list integer output equals new array list. If root equals null, return output. Q integer q equals new linked list. List root offer root, while the q is not empty. True int size equals q dot size. For int I equals 0, I has to be less than size I plus plus. Q dot tree node cur equals q dot poll. If cur dot left does not equal null, then q dot offer cur dot left. If cur dot right does not equal null, q dot offer cur dot right. And then what do I do? Here, oh, if if I equals size minus 1, then I'll put to add cur.val, return output. Oops. Tree node. Okay. Beautiful. Okay, counting the good nodes. Public int good. Public solution. Just like good equals 0. DFS root return this like good. Public int DFS tree node root. If root equals null, return. I don't even think we need this. Void. Return. And then we're gonna need integer min value. Yeah. Int prev tree. If root is less than or equal to prev. This dot good plus equals root dot val is less than or equal to prev 1 0. Prev equals math dot min math dot max root dot val prev. And then we run dfs root dot left prev dfs root dot right prev. I'm off by 1 on all of them. Is this the solution? I don't know if this is the solution. I was gonna say, there's something wrong. What was wrong with that one? This is the wrong way. There we go. Bit that up. Okay. Validate BST. So here, return validate root long. No, integer to integer dot min value, integer dot max value, public boolean validate tree node root int min int max. If root equals null, return true. If root is less than or equal to min, return, or root is greater than or equal to max, return false. Return validate root.left min or root.val, and validate root.right root.val max. Oops, root.val. It was log. Jeez. Long. Why is it long though? Because I'm so confused. Like, why is it long? I don't really get that. Because, let's see. Because we're not adding anything, right? So why would we overflow? Let me think. I'm just gonna ask GPT. Why does this overflow? That doesn't really make sense to me. Whatever. K smallest element of BST. Oh, you just do an in order, don't you? Yeah. So we have a list of integers called list equals new array list, and then we run an in order traversal on the root and the list, and we return list.get k-1. Yeah. Public void in order tree node root list integer list. If root equals null, return in order dot left list dot add root dot val in order root dot right list. There we go. Build tree. I could be flipping this, but for pre-order length map dot or this pre-order index mapping dot put pre-order return build 0 pre-order okay. Tree node equals new tree node. I definitely did this wrong. Pre-order this dot pre-order index plus plus. Okay. No dot left equals build left equals left this dot map dot get or this dot in order index mapping dot get no dot val -1 and pre-order no dot right equals build right this dot in order index mapping dot get no dot val +1. It's this then right pre-order return no
This should be good. Oh. There you go. Beautiful. Pre-order and owner traversal. This one. Okay. Max paths. Oh, this stupid problem. Wait. Return root.val plus math.max left and right, I believe. Oh. Okay. And then it's this dot max equals math.max. This dot max and then root.val plus left plus right. Let's see what happens here. There we go. Serialize helper. Okay. If root is null, string builder append return string value equals root.val. String.value of root.val string builder.append value.append serialize helper root.left string builder serialize helper root.right
string builder. Yep. Return deserialize helper. New queue. String. Arrays as list. Data.split. Yeah, something like that. Public tree node, deserialize helper, queue, string queue, string value equals queue.poll. If value equals value.equals this, return null. Tree node equals new node integer.parse int value. Node.left equals deserialize helper q. Node.right equals deserialize helper q. I think that's it. This can be void. I wonder what's wrong with that. Oh, a linked list? Oh, there we go. Okay. And now we will do daily challenge. Please be easy, please be easy. Okay, it's not that easy. Count the number of bad pairs. Okay. Oh my gosh, what is wrong with me? Okay. We have to return a long though? That makes me scared. If so, we know j is greater than I. If j minus I does not equal nums j minus nums I, counter plus one. There's no way it's this straightforward. Return counter. I'm probably gonna time limit. Yeah, I'm probably gonna time limit. Yep. Okay. So it's probably a DP problem, honestly. The pairs. The pair is 0, 1, bad pair. How do you even calculate all that? Oh, you just make sure it's sorted? Wait. Isn't this the only... Isn't this like a unique... This is a unique solution, I think. I think it always has to be like this. Are there any good pairs here? Two minus 0, 2. 3 minus 4 is -1. 2 minus 1 is 1. 3 minus... So this is a good pair. 3 and 1. I don't know how I'm supposed to do this. So if you have like a 4 here, nothing until after 4 and nothing less than 4 will work for that. I kind of get the pattern here. I don't know how to do this without generating every permutation though. That's the hard part. How do I do this? How do I do this? Jeez. Hint 1. No, it wouldn't be easy to count them. Okay, notice that j minus I nums I minus I. Zero, zero, zero. 1 minus 0 is -1. 2 minus 1 is -1. -1, -1, -1. So notice that is the same as nums I minus I. Oh wait, notice that nums I minus I does not equal nums j minus j. Nums j minus j, 2 minus 1 does not equal. Okay, a bad pair is when 2 minus 1 equals 1, and then 1 minus 0 equals 1. So that's a good pair. That doesn't really help me much. Keep a counter of nums minus I to be efficient, use a hash map. Okay. Interesting. Nums I minus I. Oh, I think I see. So map integer map equals new hash map. Let's rename this account actually. For in I equals 0, I has been nums dot length and nums dot length I plus oops, jeez. Count nums. So map dot put nums I minus I map dot count dot put nums I minus I count dot get or defaults nums I minus I 0 plus 1. Okay, so we're keeping track of that. And nums j minus j. Oh, okay. Long counter equals 0. So counter plus equals nums I minus I count dot get. I think this is it. Oh shoot. Return counter. Okay. Oh wait, that's the amount of good pairs. I'm calculating the amount of good pairs. Okay, so how do I calculate the amount of bad pairs? Okay, I'm using a hash map to do that. Okay, so what do I do with this information now? I know how many. This calculates good pairs. 1, 2, 3, 4, 5, 6, 7, 8. This honestly doesn't calculate good pairs, actually. How do we calculate permutations? I think it's factorial of the length, right? So it's... No, but I'm not even calculating the right number. Because if I know how many... Let me look at all this. Wait, maybe I am doing it right. Oh, I am doing it right. So then I need to take all the possible pairs, which is 4. How do I calculate that? 4 plus 3 plus 2 plus 1. Oh. Long permutations equals 0. I think it's permutations time plus equals I. And then you take permutations minus counter. Oh, no way! No way! There we go. Okay, those hints actually helped. Usually they don't. Okay, I see. That's crazy. Alright, let's see how many freaking problems I have done. My guess is like 60 something. Oh, 49. Okay. Cool. I gotta do stuff now. I gotta do stuff.